Hello students, in this video lecture I am going to give the proof of the result that two finite ordered sets are order isomorphic if and only if they can be drawn with identical diagrams. That is, if you are given two finite partially ordered sets or PO sets, then the result says that the two sets will be, if the two sets are order isomorphic, then they have the same hash diagram, and if the two sets have the same hash diagram, then they are order isomorphic. So this is the result that we are going to prove, but for proving this main result there is a small result or a lemma that we'll be using for proving this main result, and the lemma goes like this: if P and Q are two finite partially ordered sets, they are finite PO sets, and if psi is a map from P to Q and psi is a bijection, so if psi is mapping from P to Q is a bijection, that is psi is a 1:1 onto map, then the following three conditions are equivalent, and the three conditions are that psi is an order isomorphism. This is the first condition. This first condition is equivalent to the other two. And what are the other two conditions? That x is strictly related to y in P if and only if psi x is strictly related to psi y in Q. And the third condition is if x is covered by y in P implies and is implied by, or if and only if their images psi x and psi y also behave in the same way, that is psi x is covered by psi y in Q. So these are the three conditions, and the lemma says that these three conditions are equivalent, which means that if any one of the condition holds, then the other two also hold. And this is the case. Just to explain the whole lemma diagrammatically, this is what we have. If P and Q are two finite partially ordered sets, and if let's say I pick up an element x over here in P, then the image of x under psi will be psi x, and if I pick up another element y over here, then the image of y under the map psi is psi y. Then the result says that the three conditions are equivalent. That what are the three conditions? That if psi is already given to be a bijection, which is a 1:1 onto map. So if psi is 1:1 onto, then if x is strictly related to y, then the image psi x will also be strictly related to psi y, and if the image psi x is strictly related to psi y, then the elements are also related in that way, that is x is strictly related to y. The result is true if and only if. Also, if x is covered by y, which means that x and y are related to each other, strictly related to each other, and there is nothing in no element of P in between x and y. So if x is covered by y, then the images also behave in the same way. The image of x and the image of y also behave in the same way, that is psi x will be covered by psi y, and if the image psi x is covered by psi y in Q, then the elements also behave in the same way, which means x is covered by y in P. Now this result which I have written in the lemma, this particular result, this has been proved in my earlier two videos. We have already shown that the condition 1 implies condition 2 and condition 2 implies 1, which means that 1 and 2 are equivalent conditions. This was shown in my in one of my videos, and then again we have shown that condition 2 implies condition 3 and condition 3 implies condition 2, which means that 2 and 3 are equivalent. This was shown in another video. So in the preceding two videos, the equivalence of these three conditions has already been shown as a video made on conditions related to order isomorphism for finite partially ordered sets. So there were two parts of that video, part 1 and part 2. So for the proof of this result, one can refer to those two videos. Now coming to the main result of this particular video, in which we have to show that if two partially ordered sets are finite, then we have that if they are order isomorphic, then they have the same hash diagrams. If they have the same hash diagrams, then they are order isomorphic. So let me take P and Q to be two PO sets, two finite PO sets. So let P and Q be two finite PO sets, or finite partially ordered sets, or finite ordered sets. So finite partially ordered sets. And firstly let me suppose that P and Q are order isomorphic. So suppose P is order isomorphic to Q. So because P is isomorphic to Q, so this implies that there exists a map psi mapping from P to Q, which is an order isomorphism, or there exists an order isomorphism from P to Q. So this implies that psi mapping from P to Q, there exists an order isomorphism there exists an order isomorphism psi mapping from P to Q. So again because psi mapping from P to Q is an order isomorphism, and by the lemma we have seen that if psi is an order isomorphism from P to Q, then then the statement 1 is holding. This is statement 1, which is statement 1, which is statement 1 of the lemma, which is statement 1 of lemma, and whenever statement 1 of the lemma holds, then the other two statements also hold, which means that this statement 3 is holding. So this implies statement 3 holds, statement 3, this implies statement 3 of the lemma, statement 3 of the lemma holds, and the statement 3 of the lemma holds means, that is what happens, that is if x is covered by y in P, then this implies and is implied by that their images also behave in the same way, that is psi x is covered by psi y in Q. This is statement 3. So because statement 1 of the lemma is holding, so statement 3 of the lemma holds. Now this means that the covering relations, this means that the covering relations in P and Q, covering relations in the PO sets, covering relations in the PO sets P and Q behave identically, behave identically. This is what it means. Whenever an element is covered by another element in P, then the corresponding element, the element corresponding to x in Q is psi x. We can see if x is in P, then the element corresponding to x in Q is psi x, and if y is in P, then the element corresponding to y in Q is psi y. So whenever x is covered by y, then psi x is covered by psi y. This is what we are saying, which means that the covering relations are behaving identically in both the PO sets. So as the covering relations in PO sets P and Q are behaving identically, because this is happening, so this implies covering relations in the PO sets P and Q behave identically. This simply implies that the Hasse diagrams, of the PO sets, the Hasse diagrams of the PO sets P and Q are identical. Why are they identical? Why are the Hasse diagrams identical? Because the Hasse diagram of a PO set, Hasse diagram of a PO set is determined by the covering relations. Let us suppose the Hasse diagram is simple Hasse diagram I am drawing, something like this. These are the vertices, and these interconnecting lines, denote nothing but the covering relations. So if there are two PO sets and if their covering relations are behaving identically, if this is the PO set P, let's say, and if this is the PO set Q, let's say, and if the covering relations are behaving identically, this simply means that the lines the lines are also in the Hasse diagram, the lines are also behaving identically. The diagram is actually the same because the diagram is determined by the covering relations. These interconnecting lines between circles or the vertices are nothing but these are covering relations. So if there is a line between this element and this element, if there is a interconnecting line, which means this is a covering relation, and correspondingly the element corresponding to x in Q will be psi x, and the element corresponding to y here in Q will be psi y. So if there is a covering relation over here, there is a covering relation over here, which simply means if there is an interconnecting line over here, then there is an interconnecting line over here, which means consequently, because the covering relations are identical for both the sets, the Hasse diagrams are also same. So this proves the first part. So this proves the first part, and the first part of the result. And what was the first part of the result? The first part of the result was that if you have that P and Q are order isomorphic, then they have same Hasse diagrams. The Hasse diagrams of P and Q are identical. So this is the first part that we had to show, and now let me prove the converse part. That is, if the Hasse diagrams of P and Q are identical, we will assume this, and then we will show that P and Q are order isomorphic. So let me now prove the converse part, and let us suppose that conversely suppose PO sets P and Q have the same hash diagram, have the same diagram or the same hash diagram, have the same hash diagram, and let me call that diagram as D. Now what we have to show? We have to show that P and Q are order isomorphic. Now for every element of P, there is a circle, in the diagram D, and conversely. This is one thing that we have. And for every element of Q, there is a circle in the diagram D and conversely. Now what do we mean by saying these two lines? What is the meaning of these two lines? Suppose you have the diagram of P is let's say something like this, and because P and Q are PO sets with identical diagrams, so the diagram of Q will also be somewhat like this, which is identical to that of P. Now these are the elements, or these are the elements of P, and in the hash diagram these are actually called the circles. And for every circle that you have in the hash diagram, there is a corresponding element that you have in P. So for this particular circle, there will be some element of P which will correspond to this particular circle. Let me call that element as x1. So for this circle, let us suppose that the corresponding element is x2. For this one, the corresponding element is x3, and for this one the corresponding element is x4. So for every circle that we have in the hash diagram sorry, so for every circle that we have in the hash diagram, there is a corresponding element that we have in the PO set P. And conversely, if you pick up any element over here in the PO set P, there will be a circle in the hash diagram of P. So if you concentrate on the diagram of P and the elements of P, in a way there is a sort of 1:1 correspondence between the elements of P and the circles that you have in the diagram of P, and the diagram of P has been denoted by D. So there is a sort of 1:1 correspondence that we have between the elements of P and the elements of D. The same thing goes for the PO set Q. Now for every circle that we have in the diagram of Q, in the hash diagram of Q, there is a corresponding element of Q. So if we pick up this one, this particular circle, the diagram, there will be some particular element in Q. Let me call that element as y1. Then for this particular circle, the corresponding element will be y2. For this circle, the corresponding element is, let's say, y3. For this circle, the corresponding element is, let's say, y4. So for every circle that we have in the hash diagram Q, hash diagram of Q, which we are calling as D. So for every circle that we have in the diagram D of Q, there is a element of Q, and for every element that you pick up in the PO set Q, there is a correspondingly a circle that you have in the diagram of Q, which means that if you concentrate on this particular portion, the elements of Q and the elements of D, there is a sort of 1:1 correspondence that we have in the elements of Q and D also. So we can say, so that is, there exists a bijection, or a 1:1 onto map F mapping from P to D. D is the diagram of P. So there is a bijection or a 1:1 correspondence, or a 1:1 onto map F mapping from P to D also, and also there exists a bijection G mapping from Q to D. Now let me concentrate on Q right now. Now as G is a 1:1 onto map, because G is the bijection, so G is a 1:1 onto map from Q to D. So therefore we can talk of G inverse, which means that G inverse mapping from D to Q, this exists. This is one thing. We can talk of the inverse of G, which is G inverse. And also this inverse, G inverse not only exists, also G inverse is itself a bijection. So this is a bijection, which means that this is a 1:1 onto map. So G inverse is 1:1 and onto. Now what I do is I concentrate on these two maps, this map, the map F mapping from P to D, and the map G inverse mapping from D to Q, and I define the composite of these two maps, define psi as G inverse OF. This is how I am calling F psi as. So this is basically, this is the picture that we have. This is if we pictorially, if we try to visualize the whole situation, there are three sets in hand that we have: the PO set P, the diagram D, and the elements of the diagram D, and the PO set Q. And here if you pick up any element X over here, then there is a mapping from P to D, which takes every X over here. The mapping is F, so the image of the element X under the map F is Fx. So this is what the mapping F is doing. It is taking elements of P to D, and then correspondingly from D to Q there is the map G inverse. So G inverse takes Fx over here in Q, and under the map G inverse the image of Fx is going to be G inverse Fx, something like this. And G inverse Fx can be actually written as G inverse O Fx in terms of composite. And what is G inverse O Fx? By the notation that we are using, that is psi x, which means that this particular, if you take an element over here, so corresponding to X, the element here, the corresponding element in D is Fx, and corresponding to this element Fx, which has been labeled as Fx, the corresponding element under the map G inverse is this psi x. That is what we have. The same thing goes if we pick up any element Y over here, then the image of Y under the map F is Fy, and then again G inverse acts from D to Q. So under the map G inverse, the image of Fy is G inverse Fy, and G inverse Fy can be written as G inverse OFy, which is composite of G inverse and O, and G inverse OF we have denoted by psi. So this is actually psi y. So here Y is in P, the corresponding element to Y in D is Fy, and the corresponding element to Fy in Q is psi y. So this is what we have. So basically this, because this is a 1-1 onto map, F is a 1-1 onto map, and G inverse is also a 1-1 onto map. So the composite of two 1-1 onto maps is again a 1-1 onto map. So psi is a bijection, and for every element that you choose, for every element X that you choose in P, there will be a corresponding element in this set also, and there will be a corresponding element in this set also. So for every element Y that you choose, another any arbitrary element you choose over here, there is a corresponding element in D, and then there is a corresponding element in Q. So psi inverse, psi is a 1-1 onto map, as I said before, because psi is composite of two 1-1 onto maps, or psi is a bijection, because the composite of two 1-1 onto maps is a 1-1 onto map. So psi is a 1-1 onto map or a bijection. And also if you can see that basically what is psi doing, psi is picking up element from here, and then finally this element X is being mapped to psi x under the map psi. So psi is like this is the map psi, and here again this is how the element is being mapped. Y is being mapped to psi y under the map psi. So psi is a mapping from P to Q. So psi is a bijection from P to Q. So we have got a bijection from P to Q, and corresponding to every element that you have in P, there is an element in D, and correspondingly there is an element in Q. That also we have seen. So there is a sort of 1-1 correspondence between the elements of the PO set, the two PO sets P and Q. Now having said that, we have supposed also, because P and Q, the PO sets P and Q have same hash diagrams, they have same diagram D, therefore you have that the corresponding elements, because these are the corresponding elements, the corresponding to this, the corresponding element is this, corresponding to this, the corresponding element is psi y. So therefore the corresponding elements have same covering relations. Because if the diagrams of the hash diagrams of P and Q are same, if P and Q share the same, they have identical hash diagrams, and if every corresponding to every element over here there is a corresponding element, and also their diagrams are same, so we can say that the covering relations are also same, because every interconnecting line between circles represents a covering relation. So this means that corresponding to every covering relation that you have in P, there is a covering relation that you have in Q, between the corresponding elements. So this fact can be just mathematically written as, that is, if x is covered by y, if x is covered by y in P, then this can happen if and only if the corresponding element, the element corresponding to x over here is psi x, if and only if psi x is covered by psi y, psi x is covered by psi y in Q. So this is what we conclude. So basically psi mapping from P to Q, this is a bijection, and also we have that if x is covered by y in P, then this can happen if and only if psi x is covered by psi y in Q. And this is nothing but this is statement 3 of the lemma, which I mentioned before. Statement 3 of the lemma, which is the result that we are using for doing this main result. Statement 3 of the lemma, this is statement 3 of the lemma. If x is covered by y in P, this can happen if and only if psi x is covered by psi y in Q, where psi mapping from P to Q is a bijection. If this happens, then I know that this statement is equivalent to the first statement, which means that psi is an order isomorphism. So just using, this is the statement 3 of the lemma. So therefore by lemma 1, by lemma statement 1, because statement 1 holds, statement 1 is equivalent to statement 3. So by lemma statement 1, we have that psi mapping from P to Q, this is an order isomorphism. This means that we have been able to find an order isomorphism from P to Q, which means that we can say that P is isomorphic to Q, and that is what we had to show, which proves the converse part, that is what we had to show in the converse part, that if PO sets P and Q have the same diagram, if they have the same hash diagram, then they should be order isomorphic. So the crux of the whole discussion, whatever we have done so far, is this, that if basically this result which we have done is valid for finite partially ordered sets. So if P and Q are two finite PO sets, they are finite partially ordered sets, then we just have the crux of the whole discussion is that if P and Q are isomorphic, then P and Q have same diagrams, same hash diagrams, and converse of this result is also true, which means that if they have the same hash diagrams, then they are isomorphic. So this result is if and only if, which means that if you have to show, if you are given to finite partially ordered sets, and if you have to find out whether P and Q are isomorphic or not, so this gives me a method, this result gives me a method to find out whether P and Q are isomorphic or not. So to find out whether P and Q are isomorphic or not, if this is my problem, then what I can do is I can just draw the diagrams for P and Q, and if I find that the diagrams of P and Q are same, the hash diagrams of P and Q are same, then P and Q are isomorphic. If the hash diagrams of P and Q are not same, they are not identical, then P and Q are not isomorphic. So this important result gives me a way of finding out whether two finite partially ordered sets are isomorphic or not.